Okay. So I'd like to draw a cone. And okay, and this vertex is lying just above the center of the circular base. Okay, and this is also perpendicular. And the parameters would be, this is called the vertex of the cone. Okay, this length is called height of the cone, and this length is called the radius of the cone. Okay, radius of the base would be the radius of the cone. Okay, and this is absolutely the center of base. Okay, center of the circular base. Now this figure that I have drawn here for you is what we call as right circular cone. Okay, what is a right circular cone? It is any cone in which vertex is lying above the center of the circular base, and it is also perpendicular. Okay, that is simply what we call as a right circular cone. What about other cones? Say for example, we have now something like this. Okay, see, the vertex is lying somewhere here, but the center is lying somewhere here, center of the base. Okay, they are not tallying with each other. So this angle right here, this angle with the radius is not equal to 90 degree. Okay, so this is sorry about that. This is the radius. Again, this just a second. Let's say for example that, are you there, Nisha?
Yeah.
Okay. For example that the radius, the vertex is indeed lying over the radius. Okay, write it over here. And height perpendicular to radius. This is also one condition. Okay, let's say even if it were lying over the center, and if still the angle is not equal, this angle is not equal to 90 degree, then again this will not be called as a right circular cone. And in the previous condition that I have drawn, that if the center is not at all lying over the like vertex and center are not lying over the same vertical line, then also it is a random cone. Okay, and when would be the condition when it would not be even called a cone? When either of these surfaces, like how many surfaces are there? First of all, this surface, this circular surface, which has been bent something like this is curved, right? And the
Mm-hmm.
second surface is this surface. When either of the surfaces are irregular, then we'll call that this is like this is not even a cone. Let me show you the diagram. see here, in these figures, this cone is right circular, and this angle is 90. If this angle is not 90, this is any random cone. And if this surface, let's say for example, is irregular, even if the angle is 90 or not 90, it does not matter at all. If this surface is, if any of the surfaces, either the base or the curved surface surmounting the base, or both of them are irregular in nature, then that figure we would not call a cone. Okay?
Okay.
Any doubts? Now, there is one more thing related to cones. We copy and paste this out. So vertex. Okay. There is one more parameter related to cones, which is this length.
The slant.
Yeah. This we denote it by L, and we call it the,
Slant height.
yeah, slant height of the cone. The formula for the same we can easily calculate out with the help of this right angle triangle being formed here, in which the base is the radius r, the height is this is the height, the perpendicular is the height h, and this hypotenuse is the slant height L. Okay, let's say the radius is r, the height is h. So the formula for slant height would be L square would be h square plus r square, or L would be equal to under root h square plus r square. This would be the formula for the slant height of the cone. Okay, it's an important formula. Okay, now let's talk about the curved surface area of a cone. So let's say again we have a cone something like this. Okay, so what would be called as a curved surface area? The area of this surmounting thing, right? This whole area, this is what we'll call as the curved surface area. It means, again, for a curved surface area, what have I told you, that in the figure that has been given to you, you just assume it to be the shape of a room in which you are standing, and on the ground and the roof, those area you have to exclude for calculating out the curved surface area, right?
Yeah.
It means if you are standing like this is the ground, this circular thing is the ground, and there is no roof at all. So only this area you will have to ignore in order to find out the curved surface area of the cone. And when you will be finding out the total surface area, in the curved surface area, you will be adding only this area pi r square. Okay. Now, how to find the curved surface area of a cone? For that, let me insert a beautiful figure for you that you are able to understand it clearly. Okay. Mm, mm, mm. This figure, look at it something like this. So there was a circular figure, okay, from which we have taken out a sector, okay, something like this. And what we have done with this sector, we have simply joined these two radii with each other so that a cone has been formed. See, this is OA, this is OA, this is OB, this is OB. We have simply joined both of them and a cone has been formed. Okay?
So that's a sphere.
No, this is not a sphere, this is a circle, a 2D figure. Okay? Let's now assume that this is capital R, the radius of the circle. Let me use another color. So the radius of the circle is r, from which the sector has been cut out. Now this r is not going to be used as it is. At least as it is not going to be used because this is a circular parameter. We have to deal with cone parameters. If the cone's slant height is equal to L, if this height is equal to H, and if this is equal to R, we want surface areas and volumes in terms of these three parameters. Okay, not this one. Why? Because this is the parameter for the circle and we are not interested in that. We are interested in the cone parameters. Now, this R, this OA that has been joined something like this OA. These OA and OB are what? Well, obviously
Radius.
they are radius, but for the cone they are what?
The slant height.
Exactly. It means this R is nothing but the slant height for the cone. Okay. It means the slant height is something like this, L. Okay. And this length is what? AB is what? This
AB.
is
The
this length, the length of an R.
yeah.
What is the length of an R formula?
2 pi r and degrees over 360.
This is 2 pi R uh, theta over 360. Ah, where theta is this, right?
Yeah.
Okay. So when we are just talking about the sector that we have cut out, let's say this is the sector that we have cut out. Okay, when we are just talking about this thing, okay, when we are just talking about this thing, then what in this figure is contributing as the curved surface area of the cone? This
The
whole, see,
area of
this,
the sector.
yeah, exactly. Area of the sector is contributing as the curved surface area of the cone. Okay, because this thing AB, this is just making the circular base of the cone, right?
Yeah.
This AB is just being circular to make the base of the cone, nothing more. Okay, now how to find out the area?
Oh,
See,
pi
if
r squared and theta over 360.
yeah. Also, one more thing. This thing that I have written over here, that this is the length of the arc. This is in terms of what? This is in terms of the
R
radius
of the
of the circle.
circle, which
Yeah.
is the
And
slant
theta
height.
is also there for the circle only. It means there are no conical parameters. But we know that this arc length is going to make the circumference of the base of the cone, where this is actually equal to r. Is this okay for you? What I have written here?
Yeah.
Okay. It means this whole length is equal to 2 pi r. Okay. And this is equal to L. And for the curved surface area now, we have to find out this sector's area.
So it's just the whole area.
Yeah.
So 2 pi
So
r.
how do we find that? Let me tell you. Let's say this is O, this is A, this is B. Okay. Now we'll divide it down into infinite segments. Although they are not infinitesimally small, but you have to assume that they are infinitesimally small. Okay. Such that the base so formed here is B1, right? Because they are so small, something like this can be all this curved surface, all these bases can individually be assumed as a straight line because they are so small, right?
Mm-hmm.
So let's assume bases are B1, B2, B3, and so on. Okay, now we have to find out the area. So area of the first triangle would be, let me assume denoted by dA1. What is dA1? Very small area A1. This area. Okay, this is dA1. This would be equal to what? See, if I
Using the
just
right
draw a
triangle.
piece of this for you, okay, this is very small. This this B1 is almost equal to 0. Okay, and this is O. This is something, let's say X and Y. This length is also L, this length is also L. And when we are going to drop a perpendicular something like this length is also going to be L, right?
Oh,
Why is this perpendicular length also going to be L? How can it be like if a triangle is there, isosceles triangle, this perpendicular length is also equal to the length of the two sides? It is not practically possible. But it is possible when these are infinitesimally small. When this base is almost negligible, then all these three lengths can be same. Let me draw
okay.
a triangle for you. This is an isosceles triangle. L, L. This cannot be L, right? This cannot be L. Now let's diminish the side of the base. Now, now these three lengths are almost comparable. Not exactly, but yeah, this is now not that much smaller than L than it was in the previous case. Now let's further diminish down the length of the base. It is almost equal to, it is almost negligible. Now if we are going to drop a perpendicular from here, now can these three lengths be equal to each other? Let me
Yeah.
zoom in. Now these three can be equal to each other, right?
Mm-hmm.
Because this is almost negligible. Also, you can apply Pythagoras theorem. This is L, this is X, this base is dB. Okay, it means L square will be equal to X square plus dB square. Now, this is almost equal to, let's say, 0.000000001. Almost this is the length of dB. And what is length L? Let's say it is 2 centimeters. And this is this much centimeters. Now, if you are going to square it down, what will happen? Initially, it was what? 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the power minus 9 centimeters was it. And when you are going to square it down, it will be 10 to the power minus 18 centimeters square. And
Yeah.
with respect to this 4 centimeters square, and x square would also be somewhere in the range 3.999, something like that, then it will almost be equal to 0, right?
Yeah.
It means x square would be equal to L square. It means x would be equal to L is equal to 2 centimeters. Okay.
Okay.
So this analogy you can take a screenshot of, and then we are going to proceed with our regular discussion because I'm going to erase it.
Okay, what was saying? Okay, got it.
Okay. You have understood now that how all these three lengths are equal to L. Why?
Yeah.
Because this length, this base is infinitesimally small because we have divided this whole sector down into infinite parts like this. Okay.
Yeah.
So dA1 would be equal to, what is the area of an isosceles triangle? Half into base. Base is B1 into height. Height is L. Similarly, dA2 would be equal to half into B2 into L. Is this okay?
Yeah.
And similarly, it will go until dAn will be equal to half into Bn into L, such that B1 is equal to B2 is equal to up until Bn. All these infinitesimally small lengths are equal to each other individually, right?
Yeah.
Because they are absolutely congruent triangles. Infinite number of congruent triangles that we have divided them into. Now when we are going to add them, it will give us what? Area of sector, right? All these small areas summed up together will give us the area of the sector. Isn't that right?
Yeah.
This will be equal to half into L. Let's take common. In the brackets, what would be there? B1 plus B2 up until Bn. And now if we are doing B1 plus B2 up until Bn, it means this whole length we are talking about. Am I right? So it will be 2
Mm-hmm.
pi r.
Um,
B1 plus B2 up until Bn. It means B1 plus B2 plus B3 plus B4 up until Bn. All this whole length we are talking about, which is nothing but 2 pi r. The radius of the cone here, not the radius of this circle. Okay.
yeah.
It means this gives us area of sector is actually equal to what? Pi r L right?
Yeah.
It means the curved surface area formula for a cone is equal to pi r l. Okay, very very important formula.
So that
Again,
means the
I'm
area, like the whole would be like the same
sorry.
thing, kind of. What about the surface area of the whole cone?
Yeah, in the if the whole cone we are talking about, if the total surface area we are talking about, we'll just add the area of the base to this. Right, that is what we have been doing up until now. We first of all find out the curved surface area. Then for the total surface area, what do we ignore? We ignore the top and bottom area. So we add that in the curved surface area and we get the total surface area. So what will be this area? The bottom area, it will be pi r square. This will be TSA formula. Okay, what have I done? Again, TSA, this will be equal to CSA plus pi r square. It means pi r l plus pi r square. It means TSA is going to be nothing but pi r plus L. And again, all the parameters that would be using, that would be of the cone only. This 2 pi r into theta upon 360, this thing I have never used. Why? Because this r also I have never used. Why? Because I
It'd be
had to use
160.
only the cone parameters. Okay, and I have shown you that how a cone is formed with the help of a sector, and with the help of that area of the sector, how we have calculated it. I have proven down the formula for curved surface area. I could have directly just told you that this is the curved surface area formula, directly mug it up, but I don't want to do that. I want you to, I want to give you the complete feel how it is calculated, how it is derived, and yeah, this was the method. Okay, I know it was a bit complicated, but yeah, kindly do revise it in the like after this class once, and you will be able to get through all of it. Okay.
Yeah.
If there are any doubts at all, let's say for example you are revising it today evening, and you are having some doubts which you want to get cleared instantly, then you can directly send a text message or a voice note to Anjali, asking her to like ask the same doubt from me, and she'll forward the voice note to me, and whatever doubt is there, like from the doubt I'm talking about should be from the topic that we have studied today. Okay. So any doubts, if any doubts are there, then I'll try to like send a voice note or a solution for your doubt instantly, so that there is no hindrance in your revision. Okay.
Okay.
So kindly do revise this whole thing at least once, along with the questions on the cylinders. And tomorrow, after studying out the volume formula and all, because volume is not simple here. This pi r square, you are not integrating up until a height h. Height is changing as you are moving upwards. Okay, so we'll see the derivation for that as well. So yeah, and then we'll be doing questions on cones. So please revise this whole lecture before that, and we'll be continuing tomorrow. Okay, the same time.
Okay.
Okay, thank you for joining, Pranav. Sorry.